All right, so let's do some follow-up on this since we now know that the limiting reactant was the oxygen gas, because once we use all of this up, we stop making the water. We know that the excess reactant, which is pretty much going to be left over, is the hydrogen. Okay, because again, theoretically we can make 8 molecules of water, but we don't get them all. We can only make up to 6 molecules in reality. Okay, so the other type of question would be this: well, how much of the actual product can we make here of water? In this case, for molecule wise, well, we kind of already answered it here based on this calculation. So once you know the limited reactant, you must use him for everything else. Now to answer this type of question and every other question, use the limited reactant. Since we know that there's 3 molecules of oxygen that was started off, we know we're going to use them all. Therefore, this is how much actual molecules of water will be produced. So now the question I have here for you guys then is, what is the maximum amount of water that can be produced from this reaction? Well, the answer, as you saw there, was 6. Because why? We found out that the limiting reactant is O2 gas. So how much did we start off with? Well, it was 3 molecules of O2 gas times, here we go. We use the stoichiometric coefficient from the balanced chemical reaction, which I'll just write it up here again. So it was 2H2 gas, right, plus 1 molecule of O2 gas. Okay, then when you heat this thing up, you make 2 water molecules, gas. All right, so the ratio, I said it is 2/1 molecule of H2O over 1 molecule of oxygen. That comes from this and this guy. We don't care about the hydrogen. This cancels out, so the number was 6 molecules, okay, of water. Now, of course, later on, though, what we'll do is something we actually want to quantify in the lab, because there is no such thing as a molecule or a mole balance room scale or anything like that can measure that, because we can't count these things. Okay, but say what we do is we quantify them by measuring based off of their weights. So that's using, say, like analytical balance that measures in grams. Okay, so later on we'll convert from atoms, molecules to moles, and then moles converts to grams by using what? Molar mass. So that's the other part here. Do not forget that. Okay, so going from grams to moles, moles to grams, we use the molar mass of that substance. And of course, we still know that 1 mole of anything will be equal to Avogadro's number, 6.022 times 10 to the 23rd, okay, of those particles. All right, so the only thing we'll be using now, of course, adding to this is our multimole ratio. It goes between A's parts reaction. But for right now, we have here 6 molecules of water. It's the maximum we can make for this reaction. Another question here. How much of the excess was there for consumed? As we saw before, that we only had we had a total of 8 molecules of hydrogen that was used. We know we used all of it because we already know that the oxygen gas is the limiting reactant. So we know we gotta use it all. Okay? So there is no more oxygen present. But in order to make the water, we need some hydrogen. Now it was 8 molecules of water that we started off with, but we didn't use it all of it. Okay, we used some of it. So how do we figure it out? Well, again, start with the limiting reactant. So how much did we start off with? There were 3 molecules of oxygen gas. But this time, I'm going to do this. I'm going to convert now between oxygen gas to the excess, which is hydrogen. To do that, use the multimole stoichiometry ratio. Now it's between 1 and 2. So here we go. So it's 2 molecules, of hydrogen gas over 1 molecule of oxygen gas. Okay, and therefore this guy is cancel out. So 3 times 2 is 6 molecules of hydrogen gas, okay, is actually consumed. So notice again, we're gonna use all of it. It makes sense because why? We know that the hydrogen, okay, is what we consider our excess reactant. So we know that already. So it's gonna be something left over. Is hydrogen gas. Okay? So how much of it was actually used to make this reaction? It was only 6. Okay, so that's how we figured that one out. So that's how much was used. So another question would be this: how much of the excess therefore was unreacted or left over? Well, for that, it's kind of like log conservation of matter. If I started off with originally in the problem, we had 8 molecules of the hydrogen gas to start off with, okay? But then we consume 6 molecules, okay, of hydrogen gas, which is actually has been consumed. When we take the difference between that, when we subtract, what must be left over, okay, is literally what is unreacted, okay? So 8 minus 6 is what? There's 2 molecules of hydrogen gas left over, meaning it was not consumed in this reaction. So this shows up as well in the products. Normally we don't show it, we don't see it there, but it is there. It's been there the whole time. Same analogy as what we saw with the actual solar car. We had 1 covering, 2 of the solar cells, and we have, I think it was 2 of the motors. But what we ran out was of the wheels, okay? So same idea. So we quantify that. We know how many there are. There's 2 left over that was not used in this reaction. So again, it just goes based on the amount you started off with from the excess. Subtract what was actually consumed from the excess. Subtract the difference. That's how much is left over. Last thing here you could be asked is this: calculate the percent yield if a chemist was able to make 4 molecules of water in the lab. Now the way we work out is we talk about percent yield. A percent yield is not but a percentage. Okay, percent yield in this case is how much percent-wise, okay, that was done in the lab. Most time happens in the lab. Okay, I'm doing an experiment. Okay, so to do that, what we want to know is, well, we need the following. We need the actual amount, okay, divided by the theoretical. So how much you can actually have made. This normally comes from the reaction itself. So this is from the reaction itself. Okay, the actuals was done in the lab. So eventually, when you start doing stuff, synthesizing stuff, depending on how good you are, or maybe not so good, it depends. If you're really, really good, or something's going on, the experiment's going great, maybe you make almost all of it. Okay, but maybe you have little mistakes here and there. Something happens, it spills, something happens that you lose some of the stuff as you're transferring, then your actual goes down. But the theoretical is how much you could have made if everything was a perfect experiment. So again, it's a percentage. Percentage is parts over total times what? 100. So in this case, there we go. All right, here we go. So in the actual, this chemist here in the lab had made 4 molecules of water. And it says here in the problem, actually. So that's the actual part. That's our key words here. So 4 molecules of water over, now not theoretical though. So in that same experiment, in that same reaction right here that we saw here, the max you can make here from this reaction was 6 molecules of water. So this is our theoretical. Okay? So this is what actually is what we consider to be the total. So again, if this was a perfect place, if everything was perfectly done, basically you should have made all 6 water molecules. So in this case, the chemist should have gone all the water molecules, which should have been 6. That would have been 100%. Okay, but he didn't. Stuff happened, and it does happen. There's other side reaction that occurred you weren't expecting, so the outcome is less than what you actually expect. Okay, but that's what it is. So you have the actual is 4 molecules. The theoretical from this reaction is what you got from the max that can be produced. If it was a perfect experiment, it should have been 6. So that's the total. Water times 100. Okay, so you put that in your calculator. Okay. So you take just 4 divided by 6 times 100, and it is 66.7% yield. Okay, so that's how much you got. That's how much this chemist would actually make from that reaction. Okay, so these are the important stuff that we're talking about in this chapter. These are the type of problems, questions that we do in general chemistry. So hopefully this lecture capture video helps to kind of start you guys off in understanding how limiting reactants, excess reactant, the type of questions can be asked, how we go about approaching this can be done. The difference again, it doesn't have to be in these words, molecules. Again, we rather quantify things, actually see what this thing looks like. That means we have to convert from molecules into moles, which for us mole is just counting. Let's quantify how we gather things together, how they're grouped together. So we're counting. But again, we can't sit there and count water molecules or hydrogen molecules. Instead, is we can measure them. The way we do that is on a balance. So we have to go from moles to grams. The way we do that is molar mass. Do not forget that grams per moles. Okay. So that's the actual other way of doing this is seeing this stuff in terms of grams, and you really see and hold how much it actually would have weighed out and how much it contained in that sample. So with all that said, we'll see you in the next lecture capture video.